Hello everyone, my name is Soo-Hyun Yang. I'm a postdoc researcher at the Helmer Center for Environmental Research, UFJ. I will present the spatial patterns of competing pelagic and benthic algae in the largest Germany's national river, which based on a new basin scale model we developed for coupled complex algal nutrient dynamics. Diverse algal communities play core roles in sustaining health of aquatic ecosystems in different habitats. However, anthropogenic pressures over river basins have paralyzed good functions of different algal communities in riverine ecosystems, which manifested as eutrophication. Therefore, diverse types of water quality models with algal dynamics have been developed. Let me give a brief overview on the status quo for process-based models for river algae dynamics based on two categories. One category is a spatial scale from a single reach to the whole river network, as shown in the vertical direction. The other is the type of algae simulated, whether only one type of algae between pelagic and benthic, or both of them, as shown in the horizontal direction. Different types of the off-the-shelf models have covered a wide range of spatial scale, but focused on only one type of algae. Of course, there are models dealing with both algal communities. The simplified model developed by Jaeger and Bochard considers core physical processes related to the algal dynamics and one type of limiting nutrient at a single reach scale. On the other hand, the WASP-7 developed by US EPA includes the coupled macronutrients processes with algae in much more detailed representation. Okay, then is everything fine since the model was developed already for both algae that can grow over a river network? Absolutely not. The model is set up with too complex manner, and thus lots of monitoring data are required for calibrating model parameters and validating simulation results. However, general river basins could not satisfy the required level of monitoring data over time and space. Therefore, a model with informed simplicity is needed at the scale of entire river network. To fill the gap, we developed CANDY model, abbreviated from Coupled Complex Algal Nutrient Dynamics. Its fundamental framework mostly followed the rich-scale simplified model of Jaeger and Bochard. Key novelty of the CANDY model is to cover the scope of the entire river network and to employ parsimonious representations for the coupled hydrological, geochemical, and ecological processes. The CANDY model consists of pelagic and benthic algae, which termed as A and B respectively, and one limiting nutrient, phosphorus. Light energy is also considered. Nutrient supply at a given stream is summed between influx from point and diffuse sources over directly drained areas, and influx transported from upstream reaches. Nutrient is removed by uptake processes through algae and hyperection. Algal productions are controlled by the availability of nutrient and light resources. Aforementioned processes were quantitatively reflected as the presented governing equations. The CANDY model was formulated under several assumptions. We considered one algal taxon that can grow in both water column and riverbed habitats. Lateral influx of nutrient loss input is constant over time. hydraulic geometry variables is scaled with river discharge. Model simulation is run under steady-state river discharge and the associated hydraulic geometry characteristics. We apply the Candy model to the Weser River, which is the largest national river in Germany. In the study area, about 10% of total population lives in, and 2 cities are located. About 850 wastewater treatment plants serve most of residents by reflecting the spatial distribution of human settlements. Nearly 70% of land cover is agriculture area, which contributes a proportional fraction of total phosphorus loss input. Here, I present the results of model simulation under the median stream flow measured in May for the last 70 years. Pelagic algae concentration was getting higher as streams became larger, as clearly shown along the mainstream. In contrast, benthic algae concentration was higher in smaller streams. In-stream phosphorus concentration was likely to be lower in larger streams as the results of dilution and in-stream attenuation effects. Several local spots with higher concentration were attributed to much greater magnitude of effluent from larger wastewater treatment plants compared to the abilities of small receiving rivers in terms of dilution and attenuation. Our simulation results for both algae concentration reflected the well-known contrasting habitat preferences of the 2 algal communities in the nature. In addition to the spatial distribution, we were interested in identifying emerging patterns over stream orders. The increasing trend of pelagic algae concentration for larger streams could be quantified as a consistent rate of increase over stream orders. Hence, we found its Ortonian scaling ratio as around 2. On the other hand, benthic algae concentration was characterized as 3 distinct phases. The plateau phase with high concentration in low-order streams, and the absent phase in higher-order streams. In between them, transitional phase was manifested in intermediate streams. The decreasing trend of in-stream phosphorus concentration towards downstream also revealed the Hortonian scaling ratio as about 1.4. To evaluate the reliability of the simulated phosphorus concentration, we compare them with the monitored concentration at around 300 stations. Over larger order streams, the simulated concentrations, marked as blue color, were significantly similar with the monitored values. This indicates the pronounced effects of accumulated water and nutrient flux. In contrast, for smaller order streams, the distributions of the 2 datasets were significantly discrepant, but they overlapped over a wide range. This might be attributable to non-concurrent sampling and spatio-temporal heterogeneities in hydrological and abiotic conditions for each sampling event. We admit that the Candy model needs further improvements to reflect more diverse range of natural conditions, transient river flows, spatio-temporal dynamics of benthic habitat environments, light intensity, and a new model of water temperature are required. Moreover, to facilitate the advancement, we need consistent monitoring data, at least a minimum amount for pelagic and benthic urge concentrations, and the associated water quality parameters over a river network. We conclude mechanistic-based river network scale Candy model fully represent well-known contrasting habitat preference of the pelagic and benthic urge. Distinguished spatial patterns for the competing two urge emerge by stream orders. Abrupt benthic and pelagic algal regime shifts occurs in the mid-order streams. Furthermore, the generic framework of the Candy model is transferable to other river basins. Scenario-based simulations can be used to guide strategic management and monitoring programs for securing river water quality and aquatic habitats. If you have questions or comments on my presentation, please contact me via email or write them down in the conference section. Thank you very much for your interest.